What's up, everybody? Welcome to the 7th lecture of trig. Today we're really just going to be reviewing some concepts from algebra, and I'm going to try to keep all of this short because I really, this week, just want you focusing on reviewing for your exam Thursday. So today, like I said, it's just going to be a quick review of two different concepts from algebra to kind of prep us for section 1.7 next week. Start off with, let's talk about functions. Up to this point, I've used the word a lot, but I've not actually defined the word function. So what is a function? A function is really just an equation that says, all right, given my one x input, I'm only going to get one y output. Now this has a visual analog that we know to be the vertical line test. What this looks like pictorially is to say, or graphically, is to say, all right, I've got two different graphs of an equation, two different equations. And in the first graph, if I were to take a vertical line and move it through, at no point am I going to go through more than one point on the graph. So we move this vertical line through, we only pass the graph at one point, no matter where the vertical line is. This is a function. In the other example, we do the same thing. We get through this region right here, and we find, hey, my vertical line may go through one point, like it does right here, or it might go through 2 points, like it does right here, or it might go through 3 points. It fails what's called the vertical line test. The vertical line test is just this idea. If I took a vertical line and moved it through, is there ever a spot where that vertical line is going to pass through my graph more than once? If it does, then it fails the vertical line test. And the equation that this is a graph of cannot be a function. So, function, not a function. All right. Well, a function says, let's take an x and get to y. But what if we wanted to take a y and get back to x? What would that look like? Let's see. So let's think about what I just asked. We've got a function f of x, and it gives us a y value, right? We want to go from y back to f of x. Well, that's kind of like saying I've got this function f of x, it gives a y. I'm going to take this y value, I'm going to put it inside of another function, and it's going to give me an x value back. This is what's known as an inverse function. And the definition is really just like what I've got up here. A function, g of x, is said to be the inverse function of f of x if and only if the composition of the two functions gives you your x back. So, for the record, mathematicians don't know how to spell clearly because we use IFF to represent if and only if. It just means this is the one and only way in both directions. If this is the case, then g of x is the inverse function of f of x. If g of x is the inverse function of f of x, then this is the case. That's really what if and only if means. We move both ways. All right, so you might be asking yourself, we've got this definition. The inverse function says, I'm going to take the y value that f of x gives me, and I'm going to find out what x value gave me that y value. So what does that look like graphically? What would that look like on paper as a graph? Well, let's think about this. What we've got is we're putting in an a value and it's spitting out a b value, right? So our inverse function is going to take that b value and spit out the a value. So it's going to take in the b value and spit out the a value. Now, intuitively, what this kind of hints at, and it is in fact the case, is that the graph of our inverse function will always be the mirror image of our original function across the line x equal to y. Okay, so let's kind of break that up a little bit more. Notice here we've got this function f of x is equal to y. Notice how it kind of lies, not kind of, it does lie above this line x equal to y. Now, if we were to find the inverse function, it would be the mirror image of f of x across this line x equal to y. It would be this graph. Okay. Well, I think I see something here then. If this is the case, and I know my inverse function has to be a function, well, that means the line x equal to b is the vertical line tensor, right? Well, if x is equal to b here is our vertical line, right? So we're just moving the vertical line all the way through. And all a vertical line is x equal to a constant. Moving it through. That line in our original function corresponds to the line y equal to b. It's the horizontal line. Which brings me to my next point. Now, before I can get to this other point, I've got to answer another question. This other question is, when does a function have an inverse? Well, a function f of x equal to y has an inverse function if and only if that function is what's called injective, or otherwise known as one-to-one. So what does that mean? Well, for a function to be one-to-one, all we're saying is if f of a is equal to f of b, then a must be equal to b. That's all injectivity or one-to-one means. Okay, so we're just saying that if our function gives us the same value, then it's got to be because the x is the same. Cool. Now this gets to the point I was about to make, the horizontal line test. So let's say we've got two functions, f of x and g of x. Looking at just their graphs, we can say f of x has an inverse, and we can say that g of x does not have an inverse. And we can do that because f of x passes the horizontal line test, g of x does not. So what's the horizontal line test, right? It's the exact same idea as the vertical line test, except horizontal. So we take a horizontal line, we move it up and down, and if at any point that horizontal line goes through more than 2 points on our graph, or let me say that a different way. If it goes through more than 1 point through our graph, then it fails the horizontal line test. So what I'm saying is, check it out, got a horizontal line, I'm gonna go up through the y-axis, right? Up and down. And at no point does my horizontal line pass through more than 1 point in our function. So it passes the horizontal line test. But over here, I do the same thing, and other than 0, literally every point above the x-axis fails the horizontal line test. Well, that sucks. So then g of x doesn't have an inverse. But, and this is a huge but, we can say that if we restrict ourselves to just x equal to 0 to infinity, or negative infinity to 0, then we can come up with an inverse function. So, in general, g of x does not have an inverse function. But, if we were to restrict ourselves to just the right half, or just the left half of g of x, then we could come up with an inverse function. So we can come up with inverse functions on parts of our function, but not the entire thing. Having said all of this, there's something I wanted to point out, some notation, a note of notation. When talking about functions, we generally like to use shorthand. We do that because we don't want to write out the entire equation. So we just label out a function however we want. We can say f of x, we could say g of x, we could say h of x, we could say whatever. And if this function has an inverse, we write it using the same label, but this time we attach a -1 as a superscript. So here is f of x, here is f inverse. We also generally don't write f of y, f inverse of y. We generally write f inverse of x. And that's just because we like to call our inputs x. It's a thing, having said that, that's all I've got for y'all today, so I will let y'all go. Have a good one, guys. Okay, so I lied. There's one last thing I wanted to let y'all know. For anybody who wants a more in-depth review of this material from algebra, you can check out the algebra review page that I put together on Blackboard. It's all of my notes, all of my lecture notes from when I was lecturing algebra, or when I was giving algebra lectures, I should say. In particular, for this material, the two sets of notes that'll be of most use will be the day 6 and day 11 notes. It goes more into depth about really just this idea of functions, one-to-one, and the inverse function. Having said that, now I'll let you go.